Okay, so today one of the things you're going to learn about is actually something called the normal force. Now, the normal force exists all around you, experience it all the time. You just don't really think about it. So let's scroll down to the bottom of page 21 for a moment, and we're going to fill in a couple of diagrams down here. Here we have a bison, 700 kilogram bison lying on level ground. Now, after you went through W59, you understand this bison has weight. The weight vector points down toward the center of the earth. So if you were to draw an arrow representing the bison's weight, you would draw an arrow pointing straight down toward the center of the earth. We would call that arrow Fg. That's its force due to gravity. That's its weight, force due to gravity acting on the bison. And since it has a mass of 700 kilograms, you could turn that mass into a force due to gravity using either Big Ugly or Shouty. But in this case, since it's just lying on level ground, all bison are on Earth. So since it's on Earth, we already know little g. So you know who to holler at. Shout! You just do a little mg calculation. From your PRT, g equals fg over m. And then you rearrange it, fg equals mg. And so that one just becomes 700 times 9.81. And of course, this is easy math. And for the purposes of approximation right now, 700 times 9.81 just comes out to about 700 newtons. Of course, it's a bit less than that, about 2% less than that. 700 newtons, roughly speaking, if we assume little g is around 10. Okay, now here's the thing. If this were the entirety of the picture, the bison would not be lying on level ground. The bison would be accelerating downward. And if you recall, the acceleration downward matches the gravitational field strength if you are in free fall. So this bison should be accelerating downward at 9.81 meters per second squared. But in fact, it's sitting at rest. The only way it's sitting at rest is if there is some other force balancing this downward force. There must be an upward force of the same length. In fancy speak, we call that the same magnitude. Trying to make these really look like they're the same length. Of the same length, but the opposite direction. There is, in fact, a force up here that's balancing Fg. I'm not going to name it just yet, but that force actually is also approximately 700 newtons. It must be. Otherwise, this bison would not be lying at rest. This bison is an example right now of equilibrium. Remember talking about that. This is definitely equilibrium. And if you remember, among the many definitions we use for equilibrium, you could sleep through it was our kind of layman's easy version to help you remember how to get started. This bison may be sleeping, but you could sleep through it, or acceleration zero, or net force zero. That was one of the definitions on here, F net zero, which means all the forces balance. So in fact, in this case, just seeing that the bison is sitting there, that it has zero velocity, it is constantly at zero velocity. This thing definitely is equilibrium. The F net's definitely zero. There must be an upward force balancing it. Well, there's two questions. What is that upward force and who is providing it? Well, this Fg is coming from the entirety of the Earth. Who's providing the F upward? That F upward actually is from the ground that the bison is laying upon. That ground is pushing up. That ground is balancing out the downward force. That ground, we give a special name. We call that the normal force. The normal force, F capital N. So I'm going to come over here and label that, subscript that correctly. Fn. Not net. That's different. F big N. That's the normal force that balances out the Fg. Normal force, of course, it's a vector. You draw it with an arrow. It's exerted by solid ground. Now, the ground doesn't have to be dirt. You're sitting in a chair right now. There's a normal force on you from the chair. When you lie in bed, there's a normal force on you from the bed. When you lean on the desk, there's a normal force on your elbows from the desk. When you walk, there's a normal force up on your feet from the floor. And a force is a force is a force. So the unit is Newton, which of course fundamentally is a kilogram meter per second squared. You measure it with a scale. And the most important piece of really understanding the normal force is exactly what we said at the bottom. It is a balancing force. It's whatever the ground has to provide to keep you balanced. The direction of the normal force is always perpendicular to the ground. Now, this one's a little tricky right here. FG was a little easier. So if we come over to this piece of block of copper on a steel shelf, let's do what we'll call a free body diagram, a force diagram for the copper. Well, the copper, we're assuming the steel shelf is, on a table somewhere and the earth is down here. So if we just think of the copper alone, certainly the copper has a weight or a force due to gravity. Now, of course, the full way to figure that out would be m times g. The mass in this case is 5 kilograms. And little g, 9.81. If this 5 kilogram of copper were sitting on a steel shelf somewhere on the moon, this 9.81 wouldn't be true. We'd have to do this differently. And this roughly comes out to 5 times 10, 50 newtons. Now, in this case, since this copper is resting on the steel shelf, it is in equilibrium. And if it's in equilibrium, there must be balanced forces. There must be a force upward of the exact same magnitude. That upward force, we just call it the normal force. And it also is roughly 50 newtons. And that normal force is provided by, actually right here, the steel shelf. The steel shelf is providing a pushback that's balancing the copper. Without that steel shelf, the copper would accelerate downward at 9.81 meters per second squared. But instead, the steel shelf is stopping it and is pushing up so that it does not accelerate at all. That's what we mean by the normal force being a balancing force. And if you notice in both cases, the ground here is horizontal and the force is vertical. That's perpendicular. If you want to make a little right angle right here. Again, the ground is horizontal. The force is perpendicular. So we make our little right angle here. By the way, there is no rule. I personally like starting at the center of the object and drawing my arrows away from it. But this normal force represents 700 newtons up. You could equally draw this down here, and you could equally draw your FG arrow up here. And realize this is the exact same thing. Bring a little tip of the arrow with it. The exact same picture as what I had drawn previously. This is still 700 newtons down. This is still 700 newtons up. So it is the exact same picture. And some people prefer to draw their arrows going into the object. Some people prefer to draw their arrows coming out from the object. It's up to you. It really doesn't matter. Both are legit. Both are correct. Now, here's the thing about this balancing force. The balancing force can, it frequently does not, fortunately, but it can fail. And what I mean by that, you ever walk down the street in the city? The city, you got the sidewalks, and sometimes in the sidewalks you walk over, there's the cellar door entrances. The buildings have the, usually it's like a meat shop or something, and they have a little underground, little basement where they store things. And so you're walking along and you feel fine, da-da-da-da-da. And then you step on that. Some people just straight up avoid it. And when you step on that, you ever get a little nervous? Like you feel the ground flex beneath you and you're like, ooh, what if I fell? Everybody gets that feeling like, ooh, what if the ground gave way? What would happen? If the ground gives way, if this door fails, all of a sudden, your picture turns from FG down, force of gravity down from the earth, normal force up from the ground. If this thing were to fail all of a sudden, you would get an immediate removal of Fn, gone. And what would happen to you? Well, there would be only Fg. And at that point, you would immediately begin accelerating downward at 9.81 meters per second squared. And you may say, oh, well, you know, I'm starting out VI 0. This becomes a drop problem, right? However, drop problems get fast very rapidly. In 1 second, that meaning of acceleration, 9.81, in 1 second, your velocity would change by 9.81 meters per second. You go from 0 to 9.81. It's about 22 miles an hour. In 1 second, you're already at 22 miles an hour. And whatever's beneath you is pretty hard. Now, you're not going to fall for a second through one of these cellar doors because the ground is pretty close beneath. There's steps beneath it or whatever. However, here are a couple scenarios. Here's one, and I show you this one because, well, you may be at a college party one day, and you may be dancing at a college party. Everybody having a good time. I've certainly been at parties sort of like this, jumping around, having fun. And boom, the floor immediately just collapsed. For those people, the normal force turned to 0, just like this sketch over here.
One of ours was like, stop jumping, stop jumping. It was so loud. So
well, that's the thing. She said, stop jumping. You're right. You have to be careful when you're in a multi-story event and people are jumping and having a good time because the floor can collapse. In this particular case, a lot of people got hurt. Fortunately, no one was killed. Here's another case. So beware. You ever go to college and you're on listen, if you're going to be at a dancing party, it should be outside or it should be on the first floor when there's no basement. That's it. And you also have to beware because what if there were people down here in the basement? I think in this one, no one was in the basement, which is amazingly lucky. Here was a wedding in Israel, actually. And this was much worse. The floor collapsed, fell 2 stories, went through the next floor below. This was third floor. And in this one, I believe, almost 300 people seriously hurt. It's like 33 people killed. Yeah, this is floors collapsing, the normal force disappearing. You know, we don't often think about it happening because the floor is so supportive. And here's another one. This one is surprising because it's not even that many people. If you watch here, wow. And the thing about it is, even here where the floor starts falling away from them, look how quickly they gain speed. The end of that video is not even a second, much less than a second, and they're moving fast. So let's put it this way. You're all headed to probably either hanging out at a college party or going to a college party at some point. Beware. Beware of anything that's not on the ground level with nothing beneath it. So anyway, for our problems, fortunately, the normal force will stay in place primarily. And so let's get to the meat and potatoes of this. Here it is. In math class, by the way, the word normal means perpendicular. So here's your 2 notes related to that perpendicularity. The normal force points what we normally call up, but be careful. That's not really the way it points. It actually points perpendicular to the ground. If you were to walk over and lean on the wall, there is a normal force. So if this is the wall, here's the ground, and maybe here's you over here talking to somebody in the hallway, acting like you're cool, leaning up on the wall. As you're chatting away, actually, you are putting a force on the wall. You're pushing on the wall. But the wall is actually pushing back on your hand this way, and that wall force is a normal force. So in fact, your body weight is being pulled down here by the earth, and there's a normal force for that too. There's a separate normal force. I'll draw it over here. Remember, you can move your arrows around as long as they're the correct length and the correct direction. There's another normal force balancing your feet. So you're pushing on two different hard surfaces here. Your feet are pushing on the ground, so the ground pushes you back. That's normal force. Your hand is pushing on the wall, so the wall is pushing back, normal force. All right? But the key is that normal force is perpendicular to whatever surface is being pushed upon. So here's a picture. Here's flat ground. Normal force will be straight up. If the ground tilts, like what you see over here, then the normal force will no longer be straight up. The normal force will actually tilt with the ground. It's almost like think of the capital T. Here's the top of the T. Here's the leg of the T. The normal force will point this way. Now, you don't really need to understand this little piece of it yet. Just know it's true. We'll worry more about that in Unit 6. As the ground tilts, the normal force actually decreases. So I'm going to draw this arrow a little shorter than the first arrow. There's your normal force. And if the ground tilts even more like this, you may say, well, wait a minute, what is this acting on? You know, put a little box on there, a little box sitting on this ramp. Here's a little box sitting right here. Have that same little box sitting on the ramp over here. And as you tilt that ramp, the normal force acting on the box always stays perpendicular to the ramp. And with tilt, it actually becomes smaller and smaller and smaller. The extreme version of these three pictures right here would actually be get the ramp completely perpendicular like this. Here's your angle now. And of course, that little block, if it's just sitting next to the wall in a sense, it won't feel any normal force and it's just going to drop to the ground. Okay, so there are 4 ways you will calculate normal force, and you can do this on the homework related to this. But here they are in order of popularity. Option number 1, the easy way. If you're on flat ground and nothing else is pushing or pulling on you other than your weight, the normal force matches the gravity. We did that twice right here. That's this, these first 2. That's option 1. That's the easy way you calculate normal force. If you know the weight of the object, boom, you already know the normal. If you know its mass, turn it into weight, and then boom, you know the normal. Okay. Option 2. If you're on a ramp, then you need to there has to be a way to keep track of that decreasing of the normal force. And the way you do it is by paying attention to the angle. If you're on a ramp, the normal force is calculated by the weight still. It's still balancing against what gravity is trying to do to you. The weight multiplied by the cosine of that angle. So it's not a hard thing to do. Just do it. You know, let's come down here and look at one real quick. Here's a 20 Newton box on a ramp. 20 newtons actually it's in the unit Newton. Units tell the truth. So if it's in the unit Newton, that means that it already is its weight. So here it is. Draw your arrow straight down. Force due to gravity always pulls straight down. So the force due to gravity here is exactly now. It's not approximately. It's exactly 20 newtons because they told us that. Now the normal force, you might, try to make this straight now. The normal force, you might mistakenly think, oh, it's 20 newtons up. On level ground it would be. But here, you know, this is straight up. Put a little dashed guidance line, a reference line. The normal force here actually will tilt. It is perpendicular to the ground here, the ground being the ramp. So it will actually follow the same tilt. It will tilt at 20 degrees this way. And it's not a great drawing, but it is not 20 newtons. It is actually Fg cosine theta. So it is 20 newtons times the cosine of 20 degrees. And of course, if you do that, I believe it comes out to 18 and change, which is roughly 19 newtons, something like that. But it's less. If you tilt more, tilt up to 45 degrees, this thing will go down to like 14 newtons. Tilt up to 60 degrees, it'll go down to 10 newtons. I mean, it may fall down the ramp at that point. Anyway, so there's that second way you will calculate normal force. The third way, right now, this may feel like, wait a minute, what are you talking about here? But the third way, it's called flipping friction. So there's a friction equation. The only equation you have on PRT6 that literally has Fn in it is this one. Force of friction equals this letter here we'll talk about later. That's me. Sometimes people call it mu. It's a Greek letter. It's the coefficient of friction times the normal force. So if you happen to know force of friction, coefficient of friction, you then can easily rearrange and get the normal force. I gave you one like that on the homework. You're not going to think much about this one yet. You're just going to run the numbers. And finally, the one that we're not really going to do yet, but we will do during Unit 6, is the normal force is a balancing force. And that's really the idea we got to over here, which is something has to balance out the downward pull on the copper or on the bison. That something is a normal force. So that's similar to option 1. However, it gets more complicated when you have things pulling on it. Like if I had a rope attached to this copper shelf and I were pulling on it at an angle, kind of how you pull a sled, then something might change over here. And that whole idea of Fn as a balancing force, that's going to come into play. All right, the last one over here is the baseball. Here's a 145-gram baseball at the peak of its flight. Well, is the Earth pulling on it? It's following its trajectory. Of course the Earth's pulling on it. There's an FG. The FG is not 145 grams. The FG is not times 10, 1450 newtons. This is in grams. If we want to put this into our FG equation, you have to turn that to kilograms. So the kilograms here, of course, would be 0.145 kilograms. And then you multiply the 2 there, and you get your 0.145. Multiply by 9.81. 0.145 times 9.81. And in this case, that's going to give you roughly 1.45 newtons. Of course, it'll be a little less than that, around 1.4 newtons. What's the normal force in this one? Well, be careful. You might be inclined to just come pop a normal force on this. But is this thing touching the ground? The ground is down here somewhere. It is not touching the ground. So there is no normal force here. Don't get like normal force trigger happy where you start clicking normal force for everything. Oh, there's always an Fn. No, there isn't. No, there isn't. In fact, in this case, this is a common problem the state asks that tricks people. In this case, there is no normal force. And so this thing is not in equilibrium. So if I put an E here, equilibrium, this one is equilibrium. This one we'll see, but this one is definitely not, 100% not equilibrium. Picture over here is incomplete, so we're not going to talk about that one yet. Definitively not equilibrium. Okay? This one actually will accelerate. In fact, you know the acceleration. It's 9.81 down. That's just our projectile problem. Okay, good. So that's 23 minutes of normal force. And now you'll do W510. W510 is right here. It's one side of one sheet. So simple questions. Now don't get all worked up about what you read. Number 1, they told you the mass. Okay, what's the normal force? It's a block sitting on the ground. Well, we did that. That's the bison problem. Here they ask you to draw it with a scale. Not a hard thing. Here's a mass on a block, on a ramp. Well, how do we do that? They gave you the angle. Well, we did that right here. What's the normal force? So here they ask for the weight and they ask for the normal force. Here's a couple where you have to draw the arrows or just select the arrows. And finally, here's one that has you flip around the friction equation, where I gave you the friction and I gave you the coefficient of friction. They're weird things, but just use it for now. All right? And so that should be plenty to take care of this normal force. So that's part of your period right there.